This won't come as a shock, but Hollywood tends to take more than a few liberties when it comes to accuracy, especially as far as outer space is concerned. The fact is that the vast, almost completely unexplored territory beyond our planet is a rather complicated beast to represent, and since most Hollywood writers don't possess the prerequisite PhDs, movie outer space is sometimes more fiction than science. Now, that isn't to say that Hollywood writers aren't trying. It's just that real outer space is often far more difficult to depict than even the most outlandish of fantasy films. So today, we'll bust some myths and uncover the truth about space in movies. Get ready to separate fact from fiction. The reality of outer space is that you can't hear much of anything due to the lack of atmosphere. So any movie that depicts the roar of spacecraft engines or the boom of cosmic explosions is, well, just plain wrong. Sound propagates via molecular vibrations, using primarily air as its medium. Tightly packed air molecules collide with one another when disturbed, sort of like the chain reaction that occurs when someone in a tightly packed crowd pushes the person in front of them. Only in the case of air molecules, there is rapid oscillation back and forth, creating the wave pattern that we recognize as a sound wave. The wave moves at the speed of sound, 343 meters per second, until finding a path to our eardrums. For a good visual representation, throw a rock into a pond. Water ripples are surprisingly accurate representations of sound waves. Now throw a rock into an empty pond to see why you can't hear anything in a vacuum. Of course, if we're being nitpicky, space is not a complete void. There are some rare particles floating around, primarily gas and dust, but certainly not enough to transmit sound waves. Further, in the spirit of being nitpicky, it isn't that sound doesn't exist in a vacuum at all. The astute will have realized that technically all molecules can act as a medium for sound, including the original vibrating object itself. Take the example of an outer space anvil struck with a hammer. That ringing anvil itself is making plenty of noise. It just simply can't transfer the sound to adjacent molecules because there aren't any. On a similar note, if a tree falls in the woods and no one is around to hear it, that tree doesn't make a sound. Sound only exists by definition if there are eardrums to sense the molecular fluctuations. So without sound in space, many outer space movie explosions already have a lot to answer for. In reality, space is a silent expanse, where the only sounds are those we bring with us. First and foremost, can there even be explosions in space, given that there's no air? Well, yeah, there can be certain types of explosions in a vacuum, namely from high explosives. At their core, all explosions are simply the rapid release of potential energy. And while all rapid releases of energy tend to go boom to some extent, not all of these reactions are created the same way. The burning of black powder, for example, is referred to as deflagration, or the rapid consecutive burning of a fuel. A high explosive, on the other hand, such as C4, detonates rather than deflates. Detonation is characterized by an explosive material instantly releasing all of its energy via a shock wave. Notably, explosive shock waves travel at a much faster speed than the speed of sound propagating through atmosphere and solids in a strikingly similar way. But put the pieces together, and you'll realize that, like sound waves, shock waves don't do particularly well in a vacuum. So what we're left with is a soundless space explosion with nowhere to go. Not exactly a flaming Death Star-worthy affair. In reality, space explosions are silent and lack the dramatic flair we see in movies. Now, speaking of shrapnel, you probably noticed that flying bits of debris on Earth tend to quickly land back on the ground. In a vacuum, however, there's no air resistance standing in the way of shrapnel and a virtually infinite journey into the unknown. Or at least until the shrapnel smashes into another physical object. This means that the explosion you're seeing in outer space, perhaps hundreds or even thousands of kilometers away, may still kill you. Only it might be after a few hours, days, or weeks, though, when the shrapnel eventually plows through your spaceship. At that point, you're probably going to want to be wearing a spacesuit, lest you join the handful of others that have experienced their blood boiling in a vacuum. So, always be prepared for the unexpected in space. Depending on which film you're using as reference, landing up in space without a suit is amongst the most horrendous ways to die. Your eyeballs may burst out of your head according to Total Recall, or you may end up instantly freezing according to Mission to Mars. As far as instantly freezing in space is concerned, once again, there is no atmosphere in a vacuum, meaning that heat transfer doesn't occur as it does on Earth. On Earth, we experience temperature primarily as convection or conduction, the transfer of heat with gases such as air, or the transfer of heat with nearby solid objects. In space, the primary temperature you're going to experience is thermal radiation from nearby stars. Hence, if you're unlucky enough to be without a spacesuit, you would certainly feel cold if you were in the shadow of a planet, or hot if you were in the eyeline of a star. But key to our myth, neither temperature reaction would be very dramatic or instant. In the case of the protruding eyeballs of Total Recall, the filmmakers obviously believe that violent decompression occurs in a vacuum, but you might be astonished to learn that the human body is well capable of handling a pressure differential of 1 atmosphere. To put it in perspective, every 10 meters you dive underwater equals a 1 atmospheric pressure difference. So since you don't see scuba divers abruptly being crushed into sardine cans, you won't be exploding in outer space. There, in your lungs, on the other hand, is going to want to expand rather rapidly into your chest cavity, resulting in ruptures. But don't panic. If you breathe that air out fast enough, you should be okay. At least until the liquid in your body starts spontaneously converting to vapor via ebulism, a rather horrifying thing to imagine. It refers to a process that occurs when air pressure gets too low, consequently dropping the boiling point of liquid to room temperature. You may have heard that your blood boils in space, and that is why. It's not actually due to any changes in temperature. Regardless, the longer ebulism is allowed to occur, the more destructive it will be, resulting in swelling, bruising, and the formation of gas bubbles in your bloodstream. All rather gruesome, all not instantly fatal. Instead, you're going to die in outer space for the most obvious reason: asphyxiation. The lack of oxygen will cause you to lose consciousness within seconds, and death will follow shortly after. It's a silent, cold, and lonely end, far from the dramatic portrayals in Hollywood movies. According to more than a few Hollywood movies, stars are just massive fiery balls in space. Well, not only are stars not actually burning, at least not like a piece of paper burns, they also aren't yellow. Or they're mostly not yellow. We'll get to that in a minute. Fully understanding stars is an extremely complicated topic, so let's just do a bit of a crash course, shall we? Clouds of mostly hydrogen gas and dust particles gather in space, appearing as a nebula. The dust and gas particles within nebulas sometimes clump together, be it due to a nearby planet's gravity, or perhaps just due to natural oscillation within the cloud itself. Either way, critical mass is achieved and the particles collapse to a point. In this way, a mass is formed large enough to produce its own gravity. The new gravity, in a process called accretion, gradually drags in more dust and gas. During accretion, a number of interesting things may happen. Multiple protostars may form, as well as multiple protoplanets depending on conditions. Most important to our story today is that once a protostar gathers enough gas and dust particles, creating immense pressure and heat at the center, nuclear fusion occurs. The entire mass is then said to go nova. If you're unfamiliar with nuclear fusion, this involves atoms being forced together with such immense pressure that they fuse and create a new atom. In the case of a star, helium fuses to create hydrogen, releasing excess energy in the process. Nuclear fusion therefore generates heat and radiation as a byproduct, thus making a star hot and bright. Cold fusion, as a side note, is a hypothetical version of nuclear fusion that can occur at room temperature rather than at the millions of degrees inside a star. And let's pause here for a moment just to appreciate how misguided Star Trek Into Darkness is, where cold fusion is used to freeze a volcano into ice. Moving on, let's talk about the color of stars. The color of stars is a bit of a squirrely topic, varying depending on who you're asking. According to NASA, it's temperature that determines the color of a star. In the case of our sun, you'll have noticed it tends to appear yellow during sunrise and sunset, and somewhat bluish during peak hours. Needless to say, these perceived color variations are largely due to interference from our atmosphere. The colors implied by NASA, although accurate, are mostly only relevant assuming that you're making observations with specialized equipment. In reality, anytime you're looking at a star with your naked eye, it's only ever going to appear white or retina-searingly blindingly white, depending on how close you are. There is, after all, a reason that the windows on the International Space Station are filtered and equipped with shutters, lest the astronauts spend most of their time partially blind and very, very suntanned. And with that, let's take a moment to appreciate the true nature of stars beyond the Hollywood lens. Speaking of dangerous objects hurtling through space, Hollywood sure does love asteroid belts. And who can blame them? Flying through an asteroid belt is all the excitement of a car chase, only with the added spectacle of lasers. Or asteroid belts would be exciting if the objects weren't roughly 1,000,000 kilometers apart. Considering that the Moon is 384,000 kilometers from the Earth, barely a quarter of the distance between the average asteroids in a belt, you're probably going to be okay passing through, unless you are extremely unlucky. As to why asteroid belts themselves exist, they occur for a variety of reasons but are generally the leftovers of some or other cosmic event that took place a long time ago. In many cases, interplanetary collisions will produce asteroid fields, as is the case of our own asteroid belt. The asteroid formations between Mars and Jupiter, referred to as the main asteroid belt, came about when gravity from Jupiter interrupted the accretion of planets, causing partially formed planetesimals to collide and shatter. Most of the gathered mass was lost, but some found its way into our solar system, where it remains today. So, any danger we face from asteroids clearly isn't via crashing into them with a spaceship. But then again, that's something we've known about for a long time, most explicitly since the 1970s. Hollywood may exaggerate, but the reality of space is just as fascinating. The Voyager space probes 1 and 2 were launched in 1977. Their mission was to provide data on distant planets like Jupiter and Mars, and we now know about the active volcanoes on Jupiter's moon Io solely because of the Voyager missions. It will no doubt not shock you to learn that neither probe was in danger of crashing into an asteroid as they passed through the belt. Voyager 1 went into stellar passing into the space beyond our own solar system in August 2012, and Voyager 2 did the same thing in November 2018, making the probes the furthest man-made objects from Earth. Voyager 1 sadly stopped sending good information in November 2023, while Voyager 2 remains active and in communication to this day, continuing its journey through the cosmos. As a closing thought, it's probably fair to assume that many Hollywood filmmakers are actually aware of the information that we shared here. The problem is that Hollywood is making entertainment, not science documentaries. And thus, they're much more concerned about whether an audience understands the film rather than the film being scientifically accurate. On that note, do check out The Martian, 2001, A Space Odyssey, and The Expanse for far more realistic depictions of outer space. Thanks for watching.